All right, picking up where we left off, we were about to do sp2 type hybridization, the second type of hybridization that we're covering here. And don't worry, we're not going to cover them all. There are a lot of different types of hybridization, but we're only going to go over certain ones. Anyway, sp2 involves the hybridization of an s orbital and two of the three p orbitals in the valence shell of the central atom. And so since there are three orbitals involved, that means three regions of electrons will be on the central atom, and that makes a trigonal planar electron geometry. The shape ends up being a combination of the s orbital and two of the three p orbitals, and you end up with something like this, which sort of looks like the blades on a three-bladed fan. Ideally, the lobes will be 120 degrees apart. This is the kind of hybridization you see on the central atoms in compounds like aluminum chloride, AlCl3. We've done VSEPR analyses on that compound before, and we found that it was trigonal planar in both its electron geometry and its molecular geometry, since there are no lone pairs on the central atom. Borane, or BH3, has the same electron geometry and also the same molecular geometry. ClNO turns out to have that same geometry with the nitrogen in the center and the double bond to an oxygen and a single bond to a chlorine and a lone pair on the nitrogen. This qualifies as sp2 hybridization because the lone pair counts towards the electron geometry. So this is a trigonal planar molecule in terms of electron geometry. You got three regions of electrons on the central atom. Some other examples would be something like ethylene, or ethene is its official name now. If you look at each of the carbons separately, you'll see that each of the carbons is trigonal planar. So, one region of electrons, 2, 3. And for the carbon on the right, 1, 2, 3. So each carbon is trigonal planar, and each of the carbons, therefore, would be sp2 hybridized. Formaldehyde is yet another example where you have the carbon double bonded to the oxygen, and then the two hydrogens single bonded. You've got three regions of electrons on the carbon. The double bond is one region. Each of the single bonds is a region. So that's three regions. So it will form a trigonal planar molecule in terms of both electron geometry and also the molecular geometry. So that is sp2 hybridized. What really happens with the orbitals is that in the valence shell of something like, say, aluminum, you've got two electrons in the 2s orbital of the valence shell, and you've got one electron in one of the p orbitals of the valence shell. And the s orbital and two of the p orbitals will hybridize, and that allows these three electrons to occupy one orbital individually. So you get three sp2 hybridized orbitals, each with one electron in it, and then you still have the remaining 2p orbital up there that has not been hybridized. And this is the reason that, actually this was boron, not aluminum, but this is the reason boron or aluminum can form three bonds. It's because you have three single electrons in these hybridized orbitals, which again, remember, the hybridization doesn't occur until you're in the process of forming bonds to form a molecule. Boron atoms on their own will have this electron configuration. It's only in compounds that they have this configuration. sp3 hybridization comes next, and that is an important one because it's it's a huge part of organic chemistry, which is an entire division of chemistry. As we actually saw this example briefly at the introduction of the chapter, sp3 type hybridization involves four orbitals, an s orbital and all three p orbitals in the valence shell of the central atom. So that's four orbitals total. That means there are four regions of electrons on the central atom, and that gives you a tetrahedral electron geometry. An example of the hybridization would be for carbon. For carbon, you have 2 electrons in the 2s orbital, and then 2 electrons in the 2p orbitals, which of course occupy the p orbitals individually. And looking at this, you'd think, well, carbon should really only form 2 bonds, according to this. But it actually forms 4 bonds, and the reason is the hybridization. When you actually start forming bonds, the orbitals on the carbon atom will hybridize into sp3 orbitals. So the s orbital and all 3 of the p orbitals will hybridize into 4 sp3 orbitals of equal energy and equal shape and equal size, each of them occupied by 1 electron. And because of that, now carbon can form 4 bonds. And the arrangement, again, would be tetrahedral, which would be something like this. The way I've drawn it would look more or less like that. This is drawn very badly. You can look at the diagram in the book to get a better view of it. The stick figure diagram here shows you the locations and directions of the lobes of the hybridized sp3 orbitals, and it's oriented basically like this. The 2 straight lines. Oh, this is supposed to be dotted line. The 2 straight lines are sort of flat against the paper. The wedge is coming out and down towards you, and the dotted line, which looks kind of like a smudge now, but it's supposed to be a dotted line, is going back in away from you. Okay, so where you'll find sp3 type hybrids would be in single bonded carbons, as in CH4 or CCl4 or C2H6. The thing about carbon is that it can form chains with itself. And so what you can do is actually take a tetrahedral carbon and put it together with another tetrahedral carbon, and you can do that over and over again and get long chains. So I can take 2 tetrahedral carbons and basically remove the bond to one of the hydrogens on one of them and form a bond with the other carbon, and I get C2H6 or ethane. And ethane is just 2 single bonded carbons with 3 hydrogens on each, and each carbon is sp3 hybridized, because if you look at it, each carbon is tetrahedral. This carbon's tetrahedral. Look at the other one, that's tetrahedral also. So they're both sp3 hybridized. Also, the single bonded carbon or single bonded nitrogen, like in ammonia. If you look at ammonia, well, ammonia is basically a tetrahedron with one of the positions occupied by a lone pair. So I'll just pull this off, and we'll consider the little hole there to be on the central atom to be the lone pair. So this could represent nitrogen, with the black atom being nitrogen and the white ones being hydrogen, and H3. Notice that the electron geometry is still, actually what I'm going to do is put a bond in without an atom at the other end of it to represent the lone pair. So the electron geometry is still tetrahedral, even though the molecular geometry would be trigonal pyramid. Single bonded oxygens, like in H2O. If you wanted to look at H2O, we could actually just take off another atom, and now the 2 bonds without atoms at the other end would be lone pairs, and the 2 white atoms would be hydrogens, and the black one would be oxygen in this case. So you'll notice that the electron geometry is still tetrahedral, although when we name the molecule, we ignore the lone pairs, and what we get is bent. Also, a single bonded chlorine could be considered to be tetrahedral and is sp3 hybridized, like in HCl. And you can represent that just by taking off another hydrogen and having 3 lone pairs on the chlorine. Now the black atom would be the chlorine, and the white one would be the hydrogen, and you have 3 lone pairs on the chlorine arranged like they were in a tetrahedron, and the 4th electron region would be the bond, And so the chlorine in HCl is also has a tetrahedral electron geometry. Okay, so that's some examples of sp3. Then we graduate. We've used the s orbital in the valence shell, and we've used all of the p orbitals in the valence shell. So now we graduate to using d orbitals in hybrids or hybridization. The next step would be sp3d hybridization. So this involves the s orbital in the valence shell and all three of the p orbitals in the valence shell, plus one of the d orbitals of the valence shell. Now, of course, this is only possible for atoms that have d orbitals in the valence shell. So that would be atoms from basically the third period on down. But it's important to remember the atom doesn't have to have electrons in the d orbitals in the valence shell. It just has to have, it has to be close enough or in a situation where it's close to being able to have electrons of that level of energy so that the electrons could easily be promoted into the d orbitals of the valence shell. And that's why you have to basically be in the third period or below in order for this type of hybridization to occur. Also, you may remember this type of hybridization results in more than an octet of electrons around the central atom. So it also takes electrons that are physically large, or sorry, it takes central atoms that are physically large in order to accommodate all of those electrons. Okay, so if you're making a hybrid out of the s orbital, all three p orbitals, and a d orbital, that's 5 different orbitals that are coming together. And that means 5 regions of electrons on the central atom. And of course, that means trigonal bipyramid electron geometry. And that was this guy here. So you've got the way we normally draw it, you have an atom or a region of electrons anyway going directly up, another region of electrons going directly down, and then 3 regions of electrons spaced evenly in the horizontal plane, and they are 120 degrees apart from each other. So that's 120 degrees right there. So that is your trigonal bipyramid geometry. So it's an S and a PX and a PY and a PZ and one of the d orbitals. Okay, some examples would be PCl5. And I've done my best to draw a molecule in the trigonal bipyramid arrangement. Essentially what we've got here is the yellow atom is phosphorus, and the gray and white atoms are chlorines. And so that would be PCl5. But also some of these electron regions could be lone pairs. So SF4, sulfur tetrafluoride, also has this kind of arrangement. But remember, when you're talking about trigonal bipyramid electron geometry, not all of the positions are equal. That's why I use different color atoms for the different positions. The atoms that we normally draw pointing or horizontally are called equatorial positions, and they're spaced further apart than the atoms that go up and down, the axial positions. The axial positions have interactions at 90 degrees from other atoms, whereas in the equatorial positions, they're separated by 120 degrees, which helps. And so the first lone pair is going to go into one of the equatorial positions. Okay, so I'm going to take the atom off and leave the bond behind to represent the lone pair. And so SF4 would look something like this. Still a trigonal bipyramid electron geometry. If we ignore the lone pair, the molecular geometry of this would be called seesaw. And it might not look like a seesaw when I hold it like this, but when I put it like this, you can see that, in fact, it does go back and forth like a seesaw. All right. CLF3, or sorry, CLF3 has the same kind of electron geometry, but it has two lone pairs. And again, the second lone pair will also go to an equatorial position. So this would be ClF3. And the way I drew it is basically like this, or actually more like this. There you go. With a lone pair coming out at you and a lone pair in the plane of the paper, and a fluorine going back into the paper and one going straight up and one going straight down. Of course, for the molecular geometry, if you ignore the lone pairs, then what you get is the T-shaped molecular geometry. Okay, and then if we have one more lone pair, we get something like XeF2, xenon difluoride. That turns out to have 5 regions of electrons around the central atom, but only 2 of them are bonding regions and 3 are lone pairs. The third lone pair also goes to an equatorial position, and so you have a molecule that looks something like this, the way I've drawn it. And if you ignore the lone pairs and just look at where the atoms are, the geometry is called linear. You got a bunch of lone pairs around the central atom, but you've only got atoms that are directly opposite each other, so that would be linear. What happens in terms of the atomic and molecular, or atomic and hybridized orbitals, would be that the atom would have 2 electrons, the central atom would have 2 electrons in the s orbital of the valence shell, and 3 electrons in the p orbitals of the valence shell, which of course would occupy the orbitals individually, and then d orbitals that are empty. Okay, and the hybridization involves the s orbital and all 3 of the p orbitals and 1 of the d orbitals. And so you get you get 1, 2, 3, 4, 5 sp3d or hybrid orbitals, all of the same energy. But you've also got 4 of the 5 d orbitals that have not hybridized, and they're still there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I forgot to draw the electrons in. And since you've got now you've got 5 orbitals, all of equal energy, that each has 1 electron in it. This is how the atom can form 5 bonds, or 5 regions of electrons anyway, around the central atom. And the final type of hybridization we're going to focus on here will be sp3d2. Anything beyond that gets too complicated, and it's not common enough for us to really want to bother with. So sp3d2 involves 6 orbitals, an s orbital, 3 p orbitals, and 2 d orbitals. So that's 1, 2, 3, 4, 5, 6 orbitals in total. That means there must be 6 regions of electrons on the central atom, and that would mean that the electron geometry must be octahedral, because that's what you get. And it's called octahedral. I don't know if I ever mentioned that, but it's called octahedral because if you start filling in the sides, like a side there and a side here and a side here and a side here, you get what is essentially a 4-sided pyramid pointing upward. And if you do the same thing down here, you get a 4-sided pyramid pointing downward, and they're both stuck together base to base. That overall figure has 8 sides, or octahedral, in other words. An example of a molecule that would have this type of hybridization would be SF6, where the sulfur atom forms an sp3d2 type hybrid and ends up with 5 regions of electrons around it. And so you'd have a molecule that's something like this, with each of the outer positions occupied by a fluorine, and the central atom being sulfur. And there are also some other atoms that have this type of geometry, electron geometry. For instance, XeF4 would have a xenon in the center and 4 of the positions would be bonding positions to fluorine, and the other 2 would be lone pairs. Remember what I said about octahedral electron geometry, though. It doesn't matter where the first lone pair goes. So I'll just choose that position arbitrarily. And with one lone pair, what you get is the square pyramid molecular geometry. So, you know, fill in the size and you get a 4-sided pyramid. It does matter where the second lone pair goes, though. The second lone pair has to go directly opposite the first one, so they can get as far apart from each other as possible. And then what you've got is a square planar molecular geometry, because it's square and it's flat. But it's still an octahedral electron geometry, because for the electron geometry, you count the lone pairs of electrons. And so you could draw the XCF4 something like this, with xenon in the center and fluorines around the outside, and a lone pair above the xenon and a lone pair below the xenon. Okay, the next section is about assignment of hybrid orbitals to the central atom. And in the second line here, I kind of translate what that says, because it's not really entirely clear. What we mean by assignment of hybrid orbitals to the central atom is identifying what kind of hybridization the central atom has. Okay, so that's what that means. And of course, that can be based on the number of electron regions on the central atom, as we've already seen, or in other words, the electron geometry. If you know the electron geometry, you can go straight to the type of hybridization without knowing anything else about the molecule. The steps in doing that would be, first of all, draw the Lewis structure, because you have to do the VSEPR theory on the molecule before you can find the electron geometry. And the first step in doing the VSEPR theory is do the Lewis structure. Okay, so then you find the number of electron regions on the central atom, which you can actually find from the Lewis structure. And one region of electrons would be basically what constitutes a single region of electrons would be a single bond or a double bond or a triple bond or a lone pair. Each of these things qualifies as one region of electrons, remember? And then you determine the electron geometry from the VSEPR theory, and that will take you to the type of hybridization. So again, if there are 2 electron regions, that means the electron geometry must be linear, and that means the hybridization is sp. If there are 3 electron regions, that means the electron geometry is trigonal planar, and the hybridization must be sp2. If there are 4 electron regions around the central atom, that would imply that the electron geometry must be tetrahedral, and that implies that the hybridization must be sp3. 5 electron regions means the trigonal bipyramidal electron geometry, and that means sp3d hybridization. And 6 electron regions means octahedral electron geometry, which means sp3d2 type hybridization. And that is from figure 8.21 on page 426 or 436 in the textbook. Now, there are some exceptions to the above, as it mentions in the book. Sometimes molecules with large central atoms can have shapes that are not predicted by the VSEPR theory. And in fact, sometimes if the central atom is large, so that the electrons are far away from the nucleus, and the other nucleus of the neighboring atoms are far away also, you can actually get molecules with large central atoms having shapes that apparently don't involve hybridization. So an example would be, say, H2O. That is an oxygen atom from group 6A in the periodic table. And where's my periodic table? There it is. Oxygen's group 6A. When it forms a compound with hydrogen, it has the formula H2O. We already know that the bond angle is 104.5, which is about the same as what you would expect from a tetrahedral electron geometry. H2S, that is if you form the same type of compound but with sulfur, which is right under hydrogen or oxygen in the periodic table, H2S has a bond angle of 92.1 degrees, which is pretty close to the angle you would expect for an unhybridized p orbital, which is 90 degrees. So we've got practically no hybridization going on there in H2S. If you go down to H2Te, tellurium is in the same group as oxygen and sulfur. It's just a little bigger. The bond angle is 90 degrees, exactly what we would expect from an unhybridized p orbital. So apparently by the time you get down to tellurium, there's no hybridization involved in that molecule at all, even though H2O is sp3 hybridized, which is just kind of an interesting thing to keep in mind. 8.3 is the section on multiple bonds. We've already seen a little bit about multiple bonds already. And we're going to try to find out how to describe double and triple bonds through hybridization. We already know that a double bond, well, we already know that a single bond would be a sigma bond. A double bond would be a sigma bond and a pi bond occurring at the same time between the same two atoms. And a triple bond would be a sigma bond and a pi bond and another pi bond perpendicular to the first, all occurring at the same time between the same two atoms. And I see we're about at the time limit for this segment of the video, so I'm going to leave the rest of it for next time, but that'll give you sort of an idea of what we're going to do next. Okay, so until next time, I'll see you later.